Hello all, let us discuss suction stress concept today. So far we have discussed several extended effective stress approaches by Bishop, and later this was modified by Friedland and Morgenstern, and further Vanapalli et al. Have developed other variants of the shear strength envelopes for unsaturated soils. However, all these different approaches lead to the same approach proposed by Bishop, where the contribution of matrix section V is contributed from effective stress parameter. When the effective stress parameter varies from 0 to 1, the contribution of suction on shear strength of the soil can be estimated. However, due to the difficulties associated with the estimation of Xi parameter, that is a effective stress parameter, different approaches came up. However, they lead to the same concept as proposed by Bishop. Today, let us see a new concept proposed by Liu and Lykos in 2006 called suction stress, which should incorporate all the physico-chemical aspects and capillary forces that exist due to changes in the moisture content variation within the soils, and also due to the different particle sizes associated within the soil mass. So, in this lecture, I will introduce the suction stress, and I will also explain the suction stress characteristic curve concept for determining the effective stresses in unsaturated soils, so that we can establish failure envelopes for unsaturated soils. Before introducing suction stress, let me bring you back to Terzagh's effective stress principle. Terzaghi in 1936 proposed an effective stress concept, which is total stress minus UW. So, because the contribution of pore water pressure should be taken into consideration, so he proposed this particular equation, which is very popularly used. However, this is applicable for saturated soils. Bishop has extended this effective stress principle for unsaturated soils by introducing two stress state variables such as net normal stress and matrix suction, so that he got the effective stress parameter, and then the estimation of effective stress was possible. However, before Bishop, there were few researchers who modified the effective stress principle for saturated soils itself. This is for saturated soils. For saturated soils, our researcher Lamb in 1960 has come up with an effective stress equation for saturated soils, which is sigma minus UW minus A plus R. So, this is the repulsive force or stresses due to repulsive force, and this is attractive force. So, the attractive forces in soils are due to van der Waals attraction, and repulsive forces are due to the electrostatic repulsion between diffuse double layers of the clay particles. So, essentially for clays, so there is an additional cohesion concept which needs to be explained. So, for that they have come up with attractive force and repulsive forces. However, later by Sridharan, our Indian researcher, and Venkatappa Rao in 1973, and consequently so much of work in 1979, between 1973 and 79, they mentioned that this should be sigma minus UW minus R and plus A. So, this minus AR plus A, this repulsive force will reduce the effective stress, and this attractive force will increase the effective stress. Essentially, if you take two clay particles, which are placed at some distance, say d. Now they have negative charge on the surface due to isomorphous substitution. So therefore there are some positive ions, they are available around the clay particle. So they are held at the surface, but when there is a water, adsorbed water, there is thin films that form around the clay platelet. However, as the water content increases, the diffuse double layers grow and there is a film that exists around the individual particle. So this is positive charge and another diffuse double layer around another clay particle. So this is again positive charge. So there is a repulsion between these two individual diffuse double layers. So this repulsion leads the particles to move away from each other. So the d increases as DDL thickness increases. As DDL thickness increases. So therefore, as a particle distance increases, the effective stress should decrease. Similarly, as the particles come close to each other due to some clay water electrolyte interactions, then the attractive forces should increase, that causes increase in the effective stresses. So therefore, this is the expression that is given by Sridharan and Rao. So these are all for saturated soils. He also extended effective stress principle equation for unsaturated soils by stating that this is minus UA minus R plus A. So this is for unsaturated soils also. This is for saturated soils. So before I bring you to suction stress concept proposed by Liu and Lykos, I just want to refresh you with the existing concepts of physico-chemical forces within the soil particles. Those are considered way back in 1960s and 1970s. So what essentially the suction stress given by Liu Lykos consists is that, so the physico-chemical forces are considered in the Terzaghis effective stress principle, which are given by Lamb and Sridharan and Rao, and then these are extended similar to Bishop's principle. So that forms the suction stress concept. So let me detail about these things. Here Sridharan and all, to prove the existence of repulsive and attractive forces, they have conducted several Bock shear tests, that is direct shear tests, on several soils like on kyelinite and montmorillonite soils. So some bentonite and kaolin they have taken and they have compacted into shear box. In dry state, so this is a predetermined shear plane. You have porous plates. So soil is compacted here. At dry state, they have oven dried the soil, and after oven drying, to cool down the temperatures, they have kept it in a desiccator at RH equals to 0. So therefore, there is no adsorption of moisture that takes place. So initially the soils are at fully dry state, and then they have compacted into the Bock shear tests and they applied some normal stress, and then they sheared it. And now before shearing it, they have subjected the soil to different conditions. So all duplicate samples of same conditions, one test was conducted at air dried state, one test is conducted at fully dry state, and another tests are conducted at different pore fluids by saturating the sample with these pore fluids overnight using different dielectric fluids. So the dielectric constant of the fluids varied from very small value, say 10. For air you will have 1, so 1, 2, so 80.4, this is for water. So, this is for air and this is for water. So, in between dielectric constants are varied by choosing different pore fluids like methylene etc. So, benzene etc. So, then they saturated the sample overnight with these pore fluids, and after that they sheared the soil sample. So, the profiles they got, interestingly, tau f by sigma versus dielectric constant, they have observed that this will decrease. So, as the dielectric constant increases, this may be for water 80.4 or something, and this is for air 1. So, the tau f value increases with decrease in the dielectric constant. So, this is what they have observed, and which is expected, and further they have observed that when it is plotted tau f versus sigma for different pore fluids. So, air showed some value like this, and hexane maybe somewhat like this, and different data they got, and so this is for water and this is for air, and other pore fluids like hexane etc. are in between. Hexane and other pore fluids are here, and when you extend this, they got different cohesion intercepts. So, this cohesion intercept C1 with water, and this may be C1 dash or something. So, that considering the more Coulomb envelopes, tau f equals to C dash plus sigma dash tan phi dash at tau f equals to, so the effective stresses are C dash by tan phi dash. So, these are negative values, that means these are tensile stresses. So, these are all C dash by tan phi values, tan phi dash. So, these are the values they got, and maybe C1 dash by tan phi dash. So, these are the effective stresses when these are extended back onto negative axis. So, this is called intrinsic effective stress. And here, as the A minus R, the attractive force minus repulsive force, this value increases, the strength also increases. So, for air, the dielectric constant is 1, and the attractive forces are very high and repulsive forces are 0. So, therefore, the A minus R force is maximum for air. So, therefore, the strength is highest, and which has a very high intercept, cohesion intercept. Similarly, for water, attractive forces are minimal because particle distance is very high and repulsive forces are significantly high. Therefore, this value is minimum here, and for water the cohesion intercept is lowest. The angle of internal friction slightly varied, but approximately they are nearly constant. So, therefore, they have proved that A minus R forces would definitely influence the strength aspects. So, we need to consider in the effective stress principle. The similar approach is considered by Ning Lu and William Lykos in 2006. So, they have given the concept of suction stress. So, by considering particle scale forces for unsaturated soils. So, they considered 3 types of forces according to their work. They considered type 1 force, which consists of active skeletal forces, they propagate through soil grains, and they considered type 2. So, they are active local stresses or local forces. And type 3, which is passive particle to particle contact forces. So, the active meaning these forces do exist even without any application of loading. So, in the absence of external loads also these forces exist, and passive force means it exists only when there is an external load. So, the active skeletal force include the force due to gravity, and any external force. If you have, then they are the forces are transmitted through the skeletals of the particles. And active local force include, so the physico-chemical forces, that include van der Waal attraction, forces, diffuse double air repulsion, double air attraction, and net attraction due to cementation, and which also includes negative pore water pressure, and the capillary forces due to surface tension. So, these all are forces which are considered. So, physical forces include these three, and rest other things are active local forces. So, it includes all these forces under active local forces. So, this passive particle contact forces include short range bonds and steric repulsion. So, the bonds and steric repulsion are very short range, and they help in the particles to not penetrate one in each other. So, therefore, they exist at very short range, and so these are the forces considered for developing the suction stress characteristic curve. So, once these forces are considered, generally the type 1 and type 3 forces together they are called body forces, and type 2 force is called surface force. So, when the surface forces should be equal to the body forces at mechanical equilibrium. So, therefore, if you consider a representative volume within the soil mass, so you may have particles arranged in this particular manner. So, this may be a face to face interaction between two individual particles, and you may have one face here, another face here. So, all different particle to particle interactions are shown in this particular diagram. These are particle edges, this is also particle edge, and this is particle surface. So, here these two particles are arranged in face to face interaction manner, and this another particle, two particles are in face to face interaction, but in between there are other particles held, and this is face and this is face of the clay particle considered. So, now in this particular case, when there is an external force applied, there are several forces such as the force between edge of this particle and with this particular parallel plate. So, you may have attraction, because generally the clay particles, they are negatively charged at the surface, but edges are positive because of the broken bonds etc. They have positive at the edges. So, when there is a edge which is interacting with the face, there may be a attractive forces between these two particles at the edge to face contacts. So, these are the diffuse double layer attractive forces. Double layer attraction is between particle edge and face, and similarly here, this is here double layer attraction, and in between these two you may have double layer repulsion. So, here you may have particle to particle contact forces also. So, particle to particle contact forces, and here also you may have particle to particle contact forces. So, these two are type 3, and you have pore water pressure, and these forces may exist in the soil. But if you consider an unsaturated soil in the similar representative volume, there are two particles in face to face arrangement. So, this is one particle and this is another particle. And you may have air in between. These are 8 pockets, and this whole thing is water. So, you have air pressure UA here, and similarly here you may have contact pressures FC1, these are type 3, and because air water interface that exists, here you have capillary forces, and you will have water pressure, and here also you will have water pressure, and here you may have negative water pressure, and physicochemical forces between individual particles, diffuse double layers. You may have physicochemical forces such as the double layer attraction and double layer repulsion, and similarly here also you will have double layer attraction and double layer repulsion. Here double layer attraction you may have, and here double layer repulsion you may have for these soils. So, if we consider all these forces, you may have external force that is applied, say this is external force, this is gravity force, either under the gravity the particles are coming close to each other, or there is an external force that is applied. So, this way you have type 1 force, this is type 1, and all these are type 2, and this this one and this one is type 3. So, these many forces may exist within the soil, and here in saturated soil the pore water pressure, when we consider, which is isotropic, and the pore water pressure acts with the same value all around, because there is a continuity in the pore water pressure. But in case of unsaturated soils, because there is a discontinuity, the pore water pressure is negative, and there is a air pressure that exists, therefore there is a surface tension or contractile skin that exists between air phase and water phase. So the pore water is not isotropically acting all directions. Several forces which we consider, such as the cementation, that is particles are due to covalent or ionic bonds, covalent or ionic bonds between the cementing agent and soil particles. And similarly you have van der Waals forces, this is due to electromagnetic field interaction, electromagnetic field interaction between adjacent atoms of the approaching surfaces. So therefore this is cumulative. So generally these forces are predominant when the particle distance is less than 2 nanometer. So these are all short range, van der Waals force is short range. And cementation, covalent and ionic bonds between two individual particles. So from the cementing agent and particle, this does not depend on the water content or the particle sizes. So but the van der Waals forces depend on the particle sizes, and as the particle size decrease, that is for clays van der Waals forces are higher, and it does not depend on the water content, but due to changes in the water content the particles may come close to each other, that causes increase in the van der Waals forces. So then electrostatic repulsion or double repulsion. This I have already explained that the particles are negatively charged due to isomorphic substitution. So when the particles are formed, there is a charge deficiency within the internal structure. So because of which it attracts positive ions and onto the surface, and because of this even the water is adsorbed in the dry state, and therefore at air dried state we have seen that there is some moisture that exists. So this air dried water content for clay soils, especially bentonite or montmorillonite rich clays, is very high. It can be as high as 15 to 20% water content by weight. And attractive double layers, double layer interaction, interaction is due to EF flocculation. When the particles are arranged in this manner, this is one particle and this is another particle. So the edge of the particle, one particle, and face of the another particle, when they are interacting, so edge generally have positive charge and the face has negative charge, therefore there is an attractive force between these two particles. So these are generally EF flocculation causes these forces. Capillary forces are due to particle arrangement or structure. So when there is a capillaries within the particles, there is a surface tension force that develops, and then the water will be adsorbed, and this in turn develops forces within the soil particles. It has a very potential contribution for effective stresses at one particular water content. At very high saturations, so nearly degree of saturation is close to 100%, it does not have much role, and when the water content is nearly close to dry state where the water exists around the particles as a thin layers, then these the contribution of capillary force is negligible, but in between the contribution is significantly high. The Born and steric forces, steric repulsion, short range forces are highly dependent on the interparticle separation, as I mentioned. So therefore if this can be understood, particle size if interparticle stress are plotted, so the interparticle stress is highest when the particle size is lowest. So you have this kind of a behavior for capillary action Similarly, for diffuse double layers, and van der Waals forces, this is how they vary, and the cementation attraction is constant, it does not depend on the particle size. So, this is due to cementation, and this is double layer repulsion, and this is van der Waals force. So, this is how these forces depend on the particle sizes, and similarly how they vary with degree of saturation. Same interparticle force, this could be as high as 10 power 6 kilopascal, and the size ranges are considered 10 power 5 micrometer, and this is also 10 power 6 in interparticle force, interparticle stress. So, this is varying like 10 power minus 2 to 10 power minus 6, and this is 10 power minus 3, and degree of saturation is varying from 0 to say 100%. So, DDL repulsion may be close to 0 when the degree of saturation is 0, that means when there is no water, the repulsive forces do not exist, because diffuse double layers would not form when the water is not present. So, therefore, DDL does not form, and it increases with increase in the moisture content and reaches a constant value at 100%. And the cementation forces are constant, they do not depend on the water content. And the van der Waals forces, they decrease with increase in the water content, assuming that the particles are getting separated from each other. At very high particle interaction, the van der Waals forces are highest. Similarly, here when the particle interaction is higher, but degree of saturation is close to 0, so therefore, the water does not exist, therefore, repulsive forces decrease to 0. So, these are DDL repulsion, and this is cementation. And the capillary forces will reach very high value at some water content, and they decrease to 0 as the degree of saturation increases. So, as I mentioned, when the degree of saturation is close to 0, that means the water content is very less, then the capillary forces do not have any role to play, and when the water content is nearly saturated, then also they do not have any role to play. So, in between they have a significant role to play. This is how they vary, and this whole concept is taken from Liu and Lycos, 2006 paper. So, we have several intergranular stresses in unsaturated soils. They can be combined as like this, which is sigma c, which is equals to effective stress, that is total stress minus UA, and you have minus W also, but which are all included in sigma S dash plus sigma C naught. So, this is the total stress, and this is air pressure, and this is suction stress. The suction stress includes the capillary forces, the physico-chemical forces, and any cementation force that may exist, all are included in suction stress. So, the suction stress is similar to R minus CA forces in Sridharan and Rao or Lamb 1960, but however, so it also includes the capillary forces, cementation force, etc., but also it considers the unsaturated state. So, it has the pore water pressure which is negative, which also includes in this. So, Sridharan and Rao considers only repulsive and attractive forces, but also this one considers all other forces. So, here the sigma C naught is intergranular bonding stress, that provides cohesion to the saturated soils. So, when we take Mohr Coulomb envelopes, when we draw the Mohr Coulomb envelopes, when we plot tau versus sigma, so for saturated clays you have a intercept. So, this intercept for saturated clays when UA minus UW is equals to 0 is C naught, the intergranular bonding stress which provides cohesion. Cohesion in saturated soils. So, that is a sigma C naught, and therefore, the suction stress is understood to be interparticle forces that exists under different water contents and due to different interactions, clay water electrolyte interactions that exists between different particles, and which includes physicochemical forces, capillary forces and cementation forces or etc. All these forces are included in this. So, this is similar to the Sridharan and Rao's equation for saturated soils. So, this sigma dash is equal to sigma T minus UA UW plus R minus A. This is Sridharan and Rao 1979 or 73. This is similar to that, and therefore, suction stress is written as sigma dash sigma s dash is equals to change in physicochemical forces plus capillary forces plus xi of UA minus UW, because when you solve these equations and represent, the whole capillary forces comes out to be sigma T minus UA plus physical forces or stresses due to physical forces plus stresses due to capillary forces plus UA minus UW times 1 minus area of air phase divided by total area. So, this is the expression we get, right. So, therefore, the UW is included in this, in the suction stress. So, what we considered is this whole thing is a suction stress, but the sigma PC is written as intergranular bonding stress which provides cohesion plus change in physicochemical stresses. This is how it is written. Therefore, we get this expression sigma CS dash is equal to delta PC, delta sigma PC plus sigma capillary forces plus xi into UA minus UW, if this is xi. So, if you consider the suction stress, this considers stresses due to change in physicochemical forces and stresses due to capillary forces plus UA minus UW, matrix suction contribution. This is similar to Bishop's. So, if you consider Bishop's approach, the effective stress is nothing but sigma minus UA plus xi of UA minus UW. So, this is similar to that, except that there are physicochemical forces plus there are capillary forces. If you include these two stresses due to physicochemical forces and capillary forces, then this is nothing but what is given by Liu and Lykos in 2006. So, therefore, the suction stress is a function of matrix suction and water content, because when water content changes, these forces would change. The capillary forces change as the water content or degree of saturation changes, and similarly the physicochemical forces change, either they may be increasing or decreasing or become constant depending on the degree of saturation changes. So, therefore, the suction stress, which is a unique function of degree of saturation or a function of volumetric water content, a function of matrix suction. So, this characteristic curve representing the variation in suction stress with respect to moisture content or matrix suction is called suction stress characteristic curve. RSSCC. So we have reached to this stage. So this is called suction stress characteristic curve. So how to determine this sigma C naught? This sigma C naught is a cohesion intercept for saturated soils. So therefore, when we draw the tau f versus sigma plot, whatever the cohesion intercept we get, C dash is nothing but sigma C naught. So this is known anyways to us. This is considered to be due to physicochemical forces. So therefore, this component is known. Therefore, changes in the physicochemical forces due to changes in the moisture content can be obtained, and therefore this is how this is considered, and this therefore this is substituted here, and they obtain the suction stress. We will discuss how this suction stress characteristic curve varies with degree of saturation, or how this is dependent on soil water characteristic curve. We will learn in the next lecture. Thank you.